Section 5.2 begins with a discussion of the Riemann sum. We're revisiting that so that we can move towards something called a definite integral. And the Riemann sum is a finite version of a definite integral. First up, they've asked me to remember my Riemann sum. What we're actually going to look at is this area under the curve, and yet it's going to be a negative area because normally I had something that was above that x-axis and I was getting the area under the curve, but this is actually the area above the curve, but it is going towards that x-axis. So this is going to end up being a negative area, and it wants to, what this text is wanting you to do is kind of look at that and investigate what's going on here, because those heights are going to be negative values. As I got with the calculator, I just went ahead and threw them up here. I'm supposed to do midpoint Riemann sum from 1 to 3 with n being 4, so that delta x is going to be 3 minus 1 over the 4. So I'm going to get my width of 0.5. So if I start at 1, the next one would be at 1.5, 2, 2.5, and 3, and each of these widths being 0.5. For the midpoint Riemann sum, I have to get what's in the middle here in between 2.5 and 3, and that would be 2.75, and in between 2 and 2.5 that would be 2.25. And that is why I got these values here. The first one that I need is going to be the 1.25. So I'm going to need these heights from here to the 2.75. So let me box those in there. I'm going to find the area, using the midpoint Riemann, and it's going to be a 0.5 times each of those heights. So that would be negative 0.5625 plus and blah 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 all the way to the plus negative 6.563, and what you'll end up getting for that would be negative 6.625. And that's what you would get for the area under this curve, because what you're saying is that that area is below that x-axis, and that's what that negative means. In the B part, we're looking at a left Riemann sum from 0 to 3. So we're starting here at 0 and going to 3. They want me to partition it into 6. Delta x would then be 3 minus 0 over the 6. Once again, this would be at the 1/2, but I'm doing a left Riemann sum, so I'm going to need this point, this point, this point, this one, this one, and this one, and I would get those values. Notice that you're going to have a positive area here and combined with a negative area here. When you do that Riemann sum, what you're going to end up with is a positive and a negative contribution to that area. And so let's do area left. It's going to be 0.5 times, and those first 3 dots, well, not this one, but because that one will be a 0, but this height right here at that 0 level is a 1, plus the next height is at 0.75, and you just get those from the table, plus 0, and then these are all going to be negative, so that would be minus, and when you crunch those you'll get 1.25 minus 3 minus the 5.25, and for this area you're going to get negative 3.875. So I had some area here that counteracted with this positive area, and the net area, which is what they talk about right here, is that positive area and that negative area combined. So they would actually subtract from each other. We're defining a definite integral right here to be our Riemann sum, but I'm going to have my Riemann sum. I want the width of these little rectangles to approach 0, and that's what this is talking about. I want an infinite number of rectangles of width 0. That is the definition of a definite integral. Now let's be sure and note the limits of integration, as these are called. When I'm talking about an interval, this b is your upper limit of the integration and the a is the lower limit. Just as not all functions are differentiable, not all functions are integratable. So if we have a function that's continuous on AB or bounded on AB, and it has a finite number of discontinuities, then we can integrate it on that interval. And this just gives you an example of a function that you can integrate over. Because what it is that you're doing is you're finding the area under those curves and adding them up to get that net area. They want you to identify the limit of this particular sum, and you're looking at that sum from 1 to 3. So it makes it kind of nice. You're given the interval that you're supposed to look at it on, and notice it is, the notation is from 3 to 1 with the function here, and you integrate it with respect to x. That's what that says. And that was all we were supposed to do for that one. Well, I mean, we can look at the graph and how it represents the area under this curve. Okay, we did that. In example 3, we're supposed to look at, kind of conceptualize this area under the curve with our functions. So I used my calculator and did the 2x minus 3. There he is. They want me to find the area under the curve from 2 to 4. And they want me to use geometry to do this. So I will. This is a 2 by, and if I calculate this point, this would be at a height of 7, I think. And at 4, this is at a height of 11. That's not an 11. Okay. This is a 2 by 7. So 2 by 7, this area is 14. This height here is 4, so using the 1/2 base times height, so 1/2 times 2 times 4 would be a 4, so the area total here would be 14 and 4, which would be 18. I could also have gotten this area by evaluating the definite integral. So let's look at how that's done, just so we can do a comparison. Using the techniques I think we did in section 4.9, I will go ahead and integrate this function. This would be 2x squared over 2 plus 3x. Remember, I'm doing the derivative backwards. It's called the antiderivative. And if I take the derivative of what is sitting here, I should get that up there. And you can put the plus c on there if you like. We don't really need to, and I'll explain why, because this is evaluated from 4 to 2. And I'll go ahead and cancel this. So what I would get would be 4 squared plus 3 times 4 plus c minus, and you'll subtract off the lower limit, and we'll discuss that later, but I just want you to notice how beautiful this is. Notice that this c minus that c, these c's will cancel. So in a definite integral, we don't have to dilly around with the plus c. This would be 16 and 12, and that would be 16, 12, that would be 28, minus 4 and 6, that would be 10. This area would be 18, which is what we got here. Let's go to the next one, and on this next one I graph for you this 2x minus 6. They want me to evaluate this from 1 to 6. Oops, 6. And let me get these heights for you. At 1, this is a negative 4, and at, of course, at 3 it's 0 there, and at 6 this height is a 6. So using geometry, I'm going to do the 1/2 base times height, and this is 2, and this height here would be a 4, so this first one is area total is negative, because it's below, 1/2 times negative 4 times 2, which would be negative 4, plus this distance here is a 1, 2, 3, so it's 1/2, 3 times 6, so half of 6 is 3, so this would be a 9, so this area here would be a 5. This function is also easily integratable, so let's see what happens if I integrate the integral of from 6 to 1 of 2x minus 6 with respect to x. That gives me 2x squared over 2 again, minus 6x evaluated from 6 to 1. These cancel, leaving me with 6 squared minus 6 squared. Okay. Minus this 1 squared minus 6 times 1, and I've got a 0 here, minus, and this is 1 minus 6, which would be a negative 5, and just like magic I get the area there. Right, this is half a circle. Area of a circle is pi, oops, that's not it. Area of a circle is pi r squared. Looks to me as though I have a radius of 1 here. Area equals pi times 1 squared, but I only have half of it, so I'm going to divide this by 2, divide this by 2. My area here will be pi over 2. This particular function is not easily integratable. Alright, and now let's further note that they wanted this from 3 to 4, so they don't want this section, they just want this section. That means I only want half of my circle, so I'm going to multiply this by another half, and my area here is pi over 4. Had they wanted it from 2 to 4, then I would have had, so I probably ought to clarify this. Alright, and had they wanted it from 2 to 4, then it would have been pi over 2. Alright, moving on. Okay, this one we're just looking at graphically. They're wanting me to give the area under the curve from B to A. From B to A, that answer is a 12. From C to B, it's under the curve, so this is a negative area, so this would be negative 10. From C to A, so C to A has a negative 10 and a positive 12, so this area would be 2. Then from D all the way to B, I have a positive 8 and a negative 10, so this area would be negative 2. Next we have a definition of reversing limits and identical limits. what this says is that computing the integral from a to b, it's exactly the same as a negative, and I just flip-flop these limits of integration. So from a to b or b to a, they're just the negative of each other. If you are computing the integral at a singular point, then of course the area under that curve would be 0 by definition. So here we have some properties. This is a definition we just looked at, and this one as well. This one says that I can look at two separate functions as a sum, and we looked at this with our integrals in 4.9, but this just extends that to definite integrals where I have limits of integration. If I have a constant multiplier with my integration, it's the same as taking that constant multiplier outside. For this one, as long as this c and this one are exactly the same, when you smush them together, it's just like looking at a graph from A to B, and you have some sort of, let's just say we're looking at it like this, and we're looking at that area under that curve. It's just like looking at it, breaking it apart, and looking at it from B to C, and then C to A. So notice, and they have to be in this order. And this one just has to do with absolute value. Alright, we're going to use our properties to figure out what the value of these integrals would be. Looks like I have a constant multiplier. Constant multiplier 1 is property 4. By property 4, I can say that this is 2 times a negative 10, so this answer would be negative 20 by prop 4. I don't have something that lets me do this from 5 to 7, although I do know that from 0 to 5, I know what that is, and I could look at 0 to 7. Let's see, let's break apart. Let's do this. Let's say that 0 to 7 f of x is equal to 0 to 5 f of x plus 5 to 7 f of x. I'm forgetting my dx, sorry, that's really bad. Don't want to do that. Okay, so I could say this, and this would be by a property, which one breaks it apart? 5. So property 5. Okay. Well, I know this answer, it's negative 10. I know this answer is 3. Oh, this is the one I'm looking for. So 7, 5, f of x dx. Doing my little algebra, scooting that over to the other side. This guy is negative 13. Alright. Oh, this is the flip-flop. That's the reverse one. That's prop 2. So this would be negative 3 by prop 2. This one it's reverse, and it has a multiplier. So it's going to be 6 times the negative of whatever that this one is, which is negative 10. So this answer is just a 60. Alright, this next one has the absolute value, and I know that the net area is negative 10, but I don't know if there were any parts of this that were above and below that x-axis. So the only thing I can tell you is I can't answer this, but I can tell you that the answer is going to be at least greater than 10. So, or it's either greater than or equal to 10, but I don't know which that is without knowing a little bit more information about the f of x. So we'll just go unknown on this one, except for that that one thing where it's either greater than or equal to the 10. I do know that much. On this next one, they asked me to do a right Riemann sum. I'm not going to do that. We've done enough Riemann sums, but I will evaluate this definite integral. And then what I'm supposed to do is evaluate it both ways and then look at the answers and say to myself, oh look, they're the same answer. So I'm doing this part right here using the definite integral. I'm letting n go to infinity. I will let you, the observer here, go and do a right Riemann sum. Hopefully you've done enough of those. X to the fourth over 4 plus x evaluated from 2 to 0. I always like it when there's a 0. Then this would be 2 to the fourth over 4 plus 2 minus, and you plug in the 0 and that would be a 0 on both those two. And 2 to the fourth, I guess that would be a 4 plus 2, and this would equal 6, and I'd be all done with this one. Oh, and I'm done with this section. So if you have any question about this, see me at the Collaborate and send me an email. Thank you very much.